children. Today I am going to start a new chapter which is mechanical properties of material. In this session I will introduce you the term elasticity and all other terminologies used to explain this chapter. So shall we start? Elasticity. The elastic behavior of material plays an important role in engineering design and also constructing bridges, automobiles, ropeways, these all. So in this section we will study the elastic behavior and the mechanical properties of solids. So let us consider what is the structure of a solid. If we have to know about the elastic behavior of solid, then it can be understood by taking microscopic nature of a solid body. As it is shown here, a solid body is composed of a number of atoms or molecules, and each atom or molecule is surrounded by other atoms or molecules. These are bonded together by interatomic or intermolecular forces and stay in a stable equilibrium position. This can be visualized by taking a mode of spring ball system. As it is shown here, you can see here the balls represent atom or molecules and the springs represent the interatomic or the intermolecular forces. In this system, if any ball is displaced a little from its equilibrium position, then the springs attached to the ball will either be stretched or compressed, and because of this the restoring forces will come into play and they will bring the ball back to its original position. This accounts for elastic behavior of solid body. So you must now have understood by why does this elasticity appear in a solid body. Now let us see what is elasticity and what is plasticity. These are the two different nature of a material. So elasticity is a property by virtue of which the material tries to regain its original configuration. When deforming force, external deforming force is applied on the body, it changes its shape, it changes its size, and when that external deforming force is removed, if it comes back to its original shape and size, regains its original configuration, then the material is said to be elastic. And if it fails to do so, even after removal of external force, then the material is said to be plastic. So this is the basic nature of a material, whether it will behave as a plastic material or as an elastic material. Configuration you all must be knowing. We had discussed this about in previous chapter. Configuration is interatomic or intermolecular separation between any two consecutive atoms or molecules. So whenever this configuration is changed, it is called a change in configuration and a restoring force gets developed in the body. So this is the introduction of elasticity, how a material behaves like an elastic material. Now if we move further, but before discussing other things, first we have to be familiar with the terminologies used in this chapter, elasticity. The first thing is deforming force. So what is a deforming force? Deforming force is an external force that is applied on the body, and then due to this force the body changes its shape or its size. So deforming force is a force which if applied on a body produces a change in normal positions of the molecules of the body. So actually it changes configuration of the body. So this is responsible for configuration change, we can say. This change can be either in length or in volume or even in shape. This kind of force is called deforming force. So whenever deforming forces are applied, if the body is elastic, then of course an opposing force have to come in picture which cancels the effect of this deforming force after removal of deforming force, and that force is called restoring force. So restoring force is property of elastic material, because after removal of deforming force, there must be a force which can restore the configuration. So that force is known as restoring force, and numerically these two must be equal. So if in a question we have to write the value of restoring force, we can write its value to be equal to deforming force as well, because restoring force being the internal force, we cannot calculate its value, whereas deforming force is an external force, so it can be measured very easily. The next term we are going to use is stress. So what is stress? Whenever a deforming force is applied on a body, it changes the configuration of the body by changing positions of molecules or atoms of the body. As a result, an internal restoring force, just now I had discussed, comes into picture, which tends to bring the body back to its initial configuration. So this internal restoring force acting per unit area is stress. So stress is equal to restoring force per unit area. And as just now I had told that numerically this value is equal to the external deforming force, so mathematically it can be written as deforming force per unit area as well. But do remember that according to definition, it should be restoring force, not the deforming force. Mathematically they both are same. Now what should be the SI unit of stress? It should be, as it is force upon area, so this must be Newton per meter square, which is given a name Pascal also. In CGS system, its unit is dyne per centimeter square. And what about the dimensional formula? This should be force upon area. So dimension can be written as ml-1 t-2. If we categorize the stress, it can be categorized in 3 categories. So let us first discuss all these categories. The first one being normal stress. As the name itself suggests, it should be the normal one which acts perpendicular to the area. So if intensity of internal force is perpendicular to or normal to the cross section on which it is applied, this is called normal stress, and sometimes also it is called axial stress. So whether it is written normal or axial, it has the same meaning. That is mathematically written by perpendicular force, which is normal force upon the area. So if restoring force developed is perpendicular to the cross-sectional area chosen, then the corresponding stress is known as normal stress. It is also known as longitudinal stress. Sometimes this will be called longitudinal as well. So many names I have told you. Now this can be of 2 types. First, either it will be a tensile. So among this, the first can be a tensile stress. Now what is this tensile stress? Tensile stress is which is responsible for change in length of the body. So whenever there is an increase in length or extension of the body in direction of force applied, the stress setup is called the tensile stress. The other one being compressive stress. As the name itself suggests, that here it must be decrement in length. So this is compressive stress. If there is a decrease in length of wire or a body due to the external force applied, then the stress setup is called compressive stress. So now we know the mathematical value of stress, that has to be deforming force per unit area. This force should be perpendicular to the cross-sectional area, and if there is an increase in length, it is known as tensile stress. If there is decrement in length, it is known as compressive stress. So before moving further, let us discuss some questions based on these concepts we just learnt. The first one being 2 rods A and B, each of equal length but different materials, are suspended from a common support. Let us draw these 2 rods. Let this be the first rod, This be the second rod from a common support I have shown here. The rods A and B can support a maximum load of W1. So if this is rod A, it can support maximum load to be equal to W1, whereas B can support a maximum load equal to W2. The values are given here. If their cross-section areas are A1 and A2, then identify the stronger material. Okay, so we have to check here which one is the stronger. At first sight, it may seem that rod B is stronger because it may support a larger weight, that is 6000 Newton, whereas A can support only 600 Newton. But this is not the measurement of strength. We have to check what is the maximum stress one can bear. So for rod A, if we calculate, then sigma A, that is the stress, maximum stress, can be written by W1 upon its area, W1 being 600 and area of A being 10 millimeter square. So it will be 10 into 10 to the power minus 6 meter square. On solving this, result will be 60 into 10 to the power 6 Newton per meter square. If I calculate the same for rod B, then for B, the sigma B can be written as W2 upon A2, which will be equal to 6000 upon its area is given 1000 millimeter square. So this is 1000 into 10 to the power minus 6. That will give 6 into 10 to the power 6 Newton per meter square. Now as we can see from the results that A can support larger stress. So of course A has to be the stronger one. So A is the stronger material. So now onwards, to check strength of material, it should not only be checked by the weight which it can support, it has to be checked by the maximum stress it can bear. Now let us move further. Another stress is there which is known as shear stress. So let us see what kind of stress this is. Now first we had discussed was the normal stress. This is now shear stress. Shear stress it is also known as tangential stress, as the name itself suggests that this time the applied force is tangential to the area of cross section. So it has to be like this. If this is the block and this kind of force is applied, of course what it will do, it cannot change its length or its area. If the lower end is fixed, then it will alter the shape. The left side will be displaced by this much of angle, right also by the same angle. So this kind of change of shape takes place if the given stress is tangential. This is known as shearing stress or the tangential stress. Again, it is calculated by, generally we denote shear stress by tau. So tau can be written as delta F upon delta A. But do remember that this time the force has to be tangential and not the normal. Of course, SI unit again has to be same. That will be Newton per meter square or Pascal. And even dimensional formula has to be the same, that is m L minus 1 T minus 2. Now we can here quote some examples of shear stress. The first, a river resists shear stress across its cross-sectional area. The fibers of a shaft resist shear stress when it is twisted by an external torque. So these are the examples of shear stress. In coming topic where we will discuss about fluid, we will see that fluid cannot sustain a shear stress. Whenever a tangential force is applied, it starts flowing. Now let us do a question based on this shear stress. Assume that if the shear stress in steel exceeds about 4 into 10 to the power 8 Newton per meter square, the steel ruptures. Determine the shearing force necessary to. First we have to consider to shear a steel bolt 1 centimeter in diameter. So let us see how this can be calculated. The force applied will be, it should be equal to stress multiplied with area. So let us write the numerical values. That will come out to be 4 into 10 to the power 8 into area. That has to be because it is 1 centimeter in diameter. So area will be equal to pi into 5 into 10 to the power minus 3 and then square of this. The result will come out to be 3.14 into 10 to the power 4 Newton, which is the force applied here. For second case, we have to consider that it has to punch a 1 centimeter diameter hole in a steel plate 0.5 centimeter thick. So let us do this one. The area over which the shear stress occurs is equal to circumference of the hole times its thickness. So we can write this time area to be equal to, it should be 2 pi r multiplied with thickness, that is t. If we substitute the numerical values, this will be 2 pi into thickness is given 0.5 centimeter. So it is 0.5 into 10 to the power minus 2 into r is given 5 into 10 to the power minus 3 meter. And the answer will be 1.57 into 10 to the power minus 4 meter square. This is the area. Now we have to calculate the force, so it has to be stress multiplied with area. That will be 1.57 into 10 to the power minus 4 multiplied with 4 into 10 to the power 8, which is the given stress here. So that will be equal to 6.28 into 10 to the power 4 Newton. Let's move to next. A bar of cross section A is subjected to equal and opposite tensile force at its ends. Consider a plane section of bar whose normal makes an angle theta with the axis of bar. Let us first draw the given situation here. If this is a bar of cross-sectional area A, a force is applied at the end. So let these be the forces. It is a tensile force, so it has to be in a direction so as to increase the length of bar. So I have applied this force here on both the cross sections. Now we have to consider a section of bar whose normal is making angle theta with the axis of bar. This is the axis of bar shown here, and cross section should be like this because normal is making an angle theta with the axis. Now what will be tensile stress on the plane? In the first part we have to calculate. Now if we resolve the part of F along normal, that should be the tensile force on this plane, and if it is resolved parallel to the plane, then that will be the shearing force on the plane. So to get tensile force, we have to write F cos theta upon area, and area has to be, as this is the perpendicular area, so it should be A sec theta. That will be equal to F upon A cos square theta. For part B, we have to calculate shearing stress on this plane. So this time the force should be along the plane, tangential to plane, and we can write force F sin theta upon, again the area is same, that is A sec theta, and the answer will be F upon 2A sin 2 theta. For the third part, for what value of theta is the tensile stress maximum? As we know, tensile stress on plane has to be maximum when cos square theta will be maximum. So it has to be at theta is equal to 0 degree. For the last one, for what value of theta is the shearing stress maximum? So for shearing stress, as it is coming sin 2 theta in the expression, so it has to be maximum when sin 2 theta will be 1, and for that theta should be equal to 45 degree. So these are the two values of angle for which tensile stress and the shearing stress will be maximum. Let's proceed further. The next one is volume stress. When a solid body undergoes a change in volume without any change in its geometrical shape, then we call it the volume stress. The stress developed in the body is known as volume stress. Here it has to be like this, which I have shown here, that this body is being subjected to normal forces from all the sides. So of course there will not be any change in shape, but it will be symmetrically compressed to a smaller sphere. So this kind of stress is called volume stress. The next term we are going to use is strain. What is strain? When a deforming force is applied on a body, there is a change in configuration of the body, as already we have discussed, and the body is said to be strained or deformed, we can say. Now the ratio of this change in configuration to the original configuration is known as strain. So strain mathematically we can define as this should be change in configuration upon the original configuration. Now this configuration change can be in any form. Either it can be change in length upon original length, or it can be change in volume upon original volume, or even when shape is deformed, it has to be equal to the change in shape. So this is the strain, how it is defined mathematically, change in configuration upon the original configuration. Now again we can categorize the strain. So strain can be categorized in three types. First is the longitudinal strain. As the name itself suggests, longitudinal strain will be the strain when there is change in length. So it has to be, generally it is denoted by epsilon. So that can be written as change in length upon the original length. As you can see, this is ratio of two length terms. So it has to be unitless and dimensionless. But for this, the force applied should be perpendicular along the axis of the body. So either it can be in this way or in this way. That will change the length. But if it has to change the length, the other end should be fixed. Otherwise, if it is free to move, then on applying an external force, the body will start accelerating. So if change has to be in the length, then there must be some compression or some extension, we can say. Now let us see some numerical examples based on this. A steel wire 2 meter long is suspended from the ceiling. When a mass is hung at its lower end, the increase in length recorded is 1 centimeter. We have to determine the strain in the wire. So first, if we write the original length, that is given 2 meter. And increase in length delta L is 1 centimeter here. So it has to be 10 to the power minus 2 meter. So what will be the strain? Strain has to be this change in length upon the original length, which on solving will give 5 into 10 to the power minus 3 value. Let's see one more question. A brass rod of length 1 meter is fixed to a vertical wall at one end, with the other end keeping free to expand. So it is like this. One of the end is fixed. When temperature of rod is increased by 120 degree, the length increases by 3 centimeter. What is the strain? Now let us see. This is very tricky one, because if the rod is free to expand, so on increment in temperature, it will expand to the new length. So there will be no elastic force developed internally in it. So if elastic force is not there, there is no restoring force, then of course strain has to be equal to 0. So though there is change in length and original length is also provided, but strain will be 0 because no elastic property is being shown by the material. The next kind of strain is known as volume strain. When there is change in volume, quote the strain as volume strain. It can be written as epsilon if I am denoting for volume strain, that has to be equal to change in volume upon the original volume. The next one is shear strain. Shear strain is the strain when deforming force is tangential to the area. As I had shown earlier also, if this lower end is remained fixed and there is a kind of tangential force applied on the upper face, then it will only alter its shape. And let this angle be theta. So this theta itself is known as shear strain. That is given by theta. And of course this theta, because it is a small theta, so it can be written as tan theta as well. And then its value will be equal to, if by delta x the upper face has been displaced and L is this length, then we can write this theta to be equal to delta x upon L. This is how shear strain is calculated. With this, our today's session is complete. We discussed about all the terms that do appear while studying the chapter elasticity. In the next session, I will explain what is Hooke's law of elasticity, and then we will solve some questions. We'll see the stress-strain curve and all other things remaining. Till then, please do take good care of yourself. Goodbye.